Hi, in today's video I would like to discuss some of the parameters and some of the basic mathematics involving spur gears. I would first like to start with the absolute minimum requirements that you must meet for two gears to mesh in the first place. The first requirement is that the module of one gear is equal to the module of the second gear. And this basically means that the gear teeth have to be the same size on both gears. If you're in the inch standard system, this means that the diametral pitch of one gear has to equal the diametral pitch of the other gear. The second requirement is that the pressure angle of both gears has to be the same. And this basically says that the teeth of both gears have to have the same shape. The final requirement revolves around the distance between the two shafts on which the gears are mounted. And to compute this distance, I first want to define another parameter. This is the pitch diameter of a gear, which is sometimes also called the reference diameter, and it is equal to the module of the gear times the number of teeth of the gear. Now, if you are in the inch standard system, the pitch diameter will be equal to the number of teeth divided by the diametral pitch. And then the distance between the two shafts now has to be the pitch diameter of one gear divided by 2 plus the pitch diameter of the other gear divided by 2.
I'd like to hop back into Fusion real quick and show you again that the pitch diameter of a gear is given on the bottom end of the gear generator. And we can see that it is indeed the module times the number of teeth.
Let's now take a look at a specific example. In the last episode I created this orange gear to go on this Archimedes screw pump. And now we want to know what must we fill in for this matching gear on this output shaft so that I can transfer the power from this motor to this shaft over here. Now the module of this gear is 2.5. And so we immediately know that the other gear must also have a module of 2.5. And same for the pressure angle, that has to be 20 degrees. But how many teeth must this other gear now have in order for this to mesh? Well, the distance between these two shafts is 54 millimeters. And we also know that this gear over here has 20 teeth. And so this gear now has a pitch diameter of the module times the number of teeth. So the gear number 1 here has a pitch diameter of 20 times 2.5 is 50. But now the question is, what must the other gear be? Well, if we take a look over here, we see that 54 is equal to 50 divided by 2 plus that unknown pitch diameter divided by 2. And so we know that the pitch diameter divided by 2 of our unknown gear is 29. And so we know that the pitch diameter in total has to be 58. But now we run into a bit of a problem, because the module times the number of teeth of our second gear has to be 58. So 2.5 times something is 58. But there is no integer number that we can put here that will allow us to do this. So this gear set over here cannot actually work as long as the module is 2.5. In order to prevent such a debacle in the future, I would like to take this third requirement and rewrite it in a slightly more useful way. What I'll do first is multiply both sides by 2, and then for the pitch diameters I will write out their expressions. So the module times the number of teeth plus the module times the number of teeth. Now, these two modules must again be the same number. So we can take this module and divide both sides. So 2 times the distance divided by the module has to be equal to the sum of both tooth counts. And this now allows you a way to select a module and a matching distance between shafts, depending on which you can change and which you can't, that will actually work. So in my case, 2 times 54 divided by the module has to be, well, the total tooth count, but at least some integer. So let's call that the total number of teeth. And so 108 divided by the module has to be some integer. And so a lot of choices could be made here. We could choose a half, we could choose 1, we could choose 2, we could choose 3. One of the few options that we cannot choose here is 2.5. So going forward, I will choose the module is 3. And why I make that choice will become more apparent when I talk about all the trade-offs in gear design. If you would like to find the distances between these two shafts, you can do so in the following way. First, I rotate this shaft around so that the flat bit of the D shaft is not what I measure. I want to measure on the round end of the shaft. I then take my calipers and I simply measure between the outsides of the shaft like this. And then that measurement is 63 millimeters. And now the distance between the outsides of these shafts is 63 millimeters. But we don't want the distance between the outsides, we want the center to center distance of the shafts. And for that we have to subtract half the thickness of this shaft and half the thickness of that shaft. So in our case it'll be 63 minus 4 minus 5 is 54 millimeters. I'd like to take a closer look at this formula here because it imposes some restrictions on our choice for the teeth counts of both gears, and with that also a restriction on the gear ratios that we can choose. If we take a look back at our Archimedes screw pump and we fill in the numbers that we have, we see that the total number of teeth has to be 36. And what I will choose is that one gear will be 16 teeth and the other gear will be 20 teeth. And in that case, the gear ratio will be 16 over 20, which is 4 over 5. But let's suppose I want a slightly higher reduction. In that case, I can take this one gear and take a tooth away from it and turn it into a 15 tooth gear. But in that case, because of this expression, it is absolutely necessary that I add a tooth to the other gear. So I cannot, for example, make a 15 over 20 tooth gear, because in that case the restriction on the shaft distance doesn't work out anymore. And so I have to add this tooth to the other gear. And so the next ratio down that I can choose from the original ratio is 15 over 21. Now, if you want a little bit more granularity in this, what you can do is take this module and divide that by 2, for example. So you choose a smaller module. And in that case, the total number of teeth is increased. And in that case, you have a little bit more flexibility in choosing what gear ratio you want. I've now gone ahead and printed the gears that I was speaking of. We have one gear of 16 teeth, module 3, pressure angle 20 degrees, and the other gear, module 3, pressure angle 20 degrees and 20 teeth. Now, if I try to mesh these together, I feel that it does run, but it's a little bit clunky. It's not entirely smooth. So I want to hop into Fusion 360 now and show you why this doesn't run quite as smooth as we'd like.
We're now back in Fusion 360 with the models of the gears that I have just shown you. And if we zoom in on the contacts of the teeth, we can start seeing the problem. If we use the measure tool and we measure the distance between these two edges, we see that it is less than a micron. And in fact, if we look over here and we measure the distance between these two edges, it is in fact 0. And so this means that if there is any inaccuracy in these gears, or if the surface has any kind of roughness to it, then we will get some interference, and this will cause the gears to not run properly. Now, there are two ways to fix this. The first way is to increase the shaft-to-shaft distance a little bit. So if we go to Modify, Move Copy, and take this gear, and let's move it just a tiny bit, 0.2 millimeters. And now we actually have a healthy gap here between the teeth. The other method is to go back into the gear generator, and then we can enter this backlash parameter. Now I've already done that, so I will hide the gears that we have and unhide the gears with the backlash parameter of 0.2 millimeters. And what the backlash parameter does essentially is that it makes the teeth a slight bit thinner. And as you can see, this causes a little gap here to open up along the teeth. Now, the downside to backlash is that if we go back again to the move copy command and I try to rotate this gear, I can give it a slight rotation and it will not yet contact the other gear. So let's say the gears are in a position like this and I want to reverse direction. Well, the gear will start moving in the other direction, but its mating gear won't start moving yet because it's not yet in contact with the tooth. And only once we reach about this angle, 0.4 degrees, will the other gear actually be touched and will it actually start moving. And this notion is referred to as backlash, that you can move one gear in the reverse direction and that it takes a while before it acts on the other gear. You need backlash, however, because if you don't have any backlash, you come into the first situation that I showed you, which is where there is no space at all between the gears, and then the gears will simply bind.
I've modeled up a new set of gears, this time with the appropriate backlash parameter, and also with the mounting hubs exactly as I've shown you in the first video of this series. So what I'll do now is grab my screw pump and I'll attach the gears to the shafts. And now we have a working screw pump. In a later video, I'll show you the point of this screw pump. Subscribe.
Now that we know what the minimum requirements are for the gears to mesh and how we can meet those requirements, I'd like to talk about some of the trade-offs that you'll still need to make when deciding on your gears. And the first parameter I want to talk about is the pressure angle. Now, first of all, if you choose a larger pressure angle, you will get stronger teeth. And if you choose a smaller pressure angle, you will get weaker teeth. And I want to go into Fusion 360 again to show you why that is the case. Here we can see a gear with a pressure angle of 10 degrees. And you can see that the gear teeth look somewhat like rectangles sticking out of the circle. And if we contrast this with a gear with a pressure angle of 30 degrees, which is really on the other extreme, we see that the gear teeth look a lot more like triangles. And if there is a force now along this direction here, which is transferring the torque, then that force will create a very large bending moment in this tooth. And because the tooth of the 30-degree pressure angle gear is much more triangular, it is much more capable of dealing with that bending moment. And for this reason, a 30-degree pressure angle gear has stronger teeth. The next aspect I want to talk about is that larger pressure angle gears tend to have more backlash than lower pressure angle gears. And again, for this I have to hop into Fusion 360 to show you. Here I've modeled up a pair of gears with a pressure angle of 10 degrees. The backlash parameter is 0 millimeters, and the spacing between the centers is exactly right. So this means that if we zoom in, we will see that there is absolutely no backlash between them. And I've done the same thing for a pair of gears with a pressure angle of 30 degrees. And here too we see no backlash. But what happens now if the spacing between the shafts isn't exactly perfect? So let's move these two gears, and let's move them by just a smidge, let's say 0.2 millimeters. Now if we look at our 10-degree pressure angle gears, and we look at the distance now between the faces, we see here a distance of 0.036 millimeters, and on this end we see 0.037. And if we compare that now to the same distance but for the 30-degree pressure angle gear, we see here a distance of 0.1 millimeter plus a little bit, and on the other end we also see 0.1 millimeter. And so that distance is a lot larger than it is in the other case for the lower pressure angle. And so what we see here is that a slight deviation in shaft-to-shaft spacing has a much larger effect on the backlash if the pressure angle is larger. The next thing to think about is that if you have a higher pressure angle, the radial forces acting on the gear train will also be higher. And this too requires a little bit more explanation, but this time we'll go to the whiteboard instead.
Let's suppose you have two gears in mesh, and through one gear you put 10 Newton meters, and that gear has a pitch diameter of 200 millimeters. In that case you will get a force along the tangent here that is equal to the torque divided by the radius. In this case that force will be about 100 Newton meters. But this is not actually the force that these two gears exert on each other. The real force actually points this way. And the angle between these two forces is now equal to the pressure angle. And this leads to a very unfortunate side effect, which is that there is an additional force here that points this way. And this radial force is equal to the tangential force times the tangent of the pressure angle. And so what you see here is that this force exists in the first place, and second, that as the pressure angle grows, that force also grows. You should also know that the force on the gear teeth, the total force along this diagonal here, is equal to the tangential force, the force that actually transfers the torque, divided by the cosine of the pressure angle. And so this force too gets larger as the pressure angle gets larger. And so higher pressure angle gears have to take more force on the gear teeth, but they also exert more force pushing the gears apart. Let me show you how not to deal with that. You're now looking at the inside of my Wi-Fi tank looking forward. And over here you can see the two drive units that drive the shafts on the left and right side, which eventually turn the tracks. And the problem with these is that the mounting of the motors especially is insufficiently rigid. And because these are 25-degree pressure angle gears, when they are turning and when the transmitted torque is maximum, there is a lot of force driving these two apart. And the problem you run into then, and when you look at an old version of the motor housing, is that there's just not enough material here to keep the motors in place. And so the motor will actually move away from the other gear slightly, away from the other shaft, and that causes the gears to come apart from each other. And when you look at that, what essentially happens is that the gear teeth will skip like this. And that creates an enormous amount of noise, an enormous amount of wear, and the tank actually doesn't move either. So it's all bad, and the way to prevent this is by ensuring that the bearing housings over here and the motor housings are both sufficiently rigid and that they are also rigidly mounted in such a way that they cannot come apart. And so for this reason, it is also very important that you choose a stiff material to make these housings out of.
Considering all the aspects that we have discussed, I would say that a smaller pressure angle gear is especially suitable for precise positioning applications. So if you need to put a part in a specific position as precisely and as repeatably as possible, you would go for a low pressure angle gear. On the other hand, if you need to transmit a lot of torque, a lot of power as well, then it will probably be better to choose a larger pressure angle. And this is especially the case if you are looking at a vehicle application. If your motor has to propel a vehicle, then frankly you don't care about the backlash that much, but you do care about making sure that the gears can withstand all the torque that you wish to transmit. Finally, I should note that there are 3 standard values for the pressure angle for gears that you can buy. The most common of these values is 20 degrees, which is most general purpose gears. The second most common value that you will find is 14.5 degrees, which is again for more precision applications and also in some cases in older machinery. And finally, 25 degrees is honestly quite rare, but that would again be for very large torque applications. Outside of these 3 values, in my experience, there is nothing really for sale. Though if you are 3D printing your own gears, then frankly nothing stopping you from using whatever pressure angle you like. The other parameter that you'll have to decide on is the module. Now we've already seen that for a gear of a given size, if you have a larger module, then you also have fewer teeth. The primary advantage to having a larger module, larger teeth, is that the teeth are stronger, so you can transmit more torque. We have also seen though that if you have a fewer total number of teeth on your gears, that also means that you have fewer gear ratios to choose from. Now most gear manufacturers introduce some backlash into their gears so that they will run properly, as we've discussed. But they introduce more backlash for gears that have a larger module, generally speaking. The other thing is that we have discussed a few times the distance between 2 shafts, and if the module is larger, you can get away with a larger error in the distance between the 2 shafts. So I'd like to go into Fusion again and show you how that works. I have 2 gears here with a module of 10. And hidden I have 2 gears with a module of 1 mm. And these gears should be spaced 200 mm apart, but they are spaced 202 mm apart. And because of this, as we've seen before, we end up with a little bit of backlash between the teeth. But if we now change our view to the module 1 gears, we see that the teeth no longer mesh at all. And so instead of having a little bit of backlash to deal with, we end up with a set that simply does nothing. The final thing you should consider is that you can only go so low with the number of teeth. Now the absolute minimum number of teeth for gears to work, as far as I know, is 7 teeth. But most stores that sell gears with a minimum number of teeth of 12 and in rare cases 11 teeth. And finally, there is a requirement for if you want gears without any undercut. So if you want no undercut with a 14.5 degree pressure angle, you need 32 teeth or more. For 20 degree pressure angle, you need 18 teeth or more. And for 25 degree pressure angle, you need 12 teeth or more. And I'd like to go into Fusion again to show you what exactly undercutting means and why you would want to avoid it. I have 2 gears here, one with 10 teeth and one with 30 teeth. And if we zoom in here on the mating section, we see that the shape of the teeth is actually slightly different. If we follow the contour of this tooth, we see that it just gets wider and wider and wider, and at the base here, where it meets the rest of the gear, the tooth is the widest. But that is not what we see with a small number of teeth. So here we see that the tooth is getting wider and wider, but it reaches its maximum around here. And then it actually gets slightly narrower. Now I've set these gears up with a motion link between them and the appropriate joints, so that if I turn them, the other one turns as well. And if we now zoom in here, we can actually see, if we look at this tooth over here, you can see that as I bring that into mesh, that undercut here, this part where the tooth gets thinner towards the base, is actually absolutely required for this meshing to work. And so this is called undercutting, where this gear tooth gets thinner towards the base. And undercutting is, as I've shown you, a necessary part for making this meshing action work, but at the same time it also reduces the strength of the gear, because right where the stress is really maximum is also where the tooth actually becomes slightly thinner. So here we see a distance of about 4 millimeters, and yet if we look at the other gear, we see a distance of about 5.5 millimeters. And so we see here that the tooth count 30 gear has thicker teeth at the base than the tooth count 10 gear. And so this is undercutting. This causes the gear teeth to be a little bit weaker. And sometimes it doesn't matter, sometimes you just have to accept that, but it is something to be aware of. I've talked a lot in this video about the distance between shafts and why it is important to get that dimension right. But there are two other errors that you can make with the shafts that lead to many of the same problems. In this first example, I'd like to show you a concentricity error, sometimes called a radial runout error. And so if I look at this hole here through this gear, I have made it a millimeter off center. So the hole should be over here at the origin, but instead it's a millimeter to the side. And this leads to two problems at the same time. Here we see that we have a little bit of interference between the green gear and the red gear. And yet if I rotate the set halfway around, we see the opposite. We see a lot of backlash. So due to this concentricity error, we now get both problems at the same time. The other problem you can run into is axial runout. And what happens here is that the axis of rotation, or the hole through the gear, is not parallel to the teeth. So if I look at this from the side and I rotate the gear, you can see that the right gear is wobbling. Now if I put this gear in the right position, and I enable the section analysis, we can take a closer look at the mating surfaces of the gear. So in green here we have the gear with our axial runout problem, and in orange we see the section of the gear which is completely fine. And if we look closely at this, we see here again this angle between the green gear and the orange gear. But we see here at the bottom that the two gears are making contact, which is nice. But if we look up, then we see here a gap between the two gear teeth. And so what happens here is that all of the stress that results from the transmitted force between these two teeth is born here at the bottom, and so the top isn't contributing to the strength of the teeth. And this will lead to a very quick premature failure of the teeth if the stress is quite high.
Coming back to our Archimedes screw pump, why did I choose a module of 3 for these gears? Well, let's take a look at our options. Remember that the total number of teeth is 2 times the distance divided by the module. So in this case it's 108 millimeters divided by the module. And so what options do we have? Well, let's say that we go for a module of 4. In that case, we have a total number of teeth of 27. In this case, for 3, we get a total number of teeth of 36. And let's say as another option we would choose 2. In that case, we would get 54. So remember that I chose this over here and that in particular I went for a gear of 16 teeth plus a gear of 20 teeth. And as we've seen in the previous slides, a 16 tooth gear has a little bit of undercutting, and a 20 tooth gear has no undercutting at all, at least not for the 20-degree pressure angle that we have here. So a module 3 would have the largest teeth that I can get away with while having only a little bit of undercut. If I went for the module 4 gear, then I would have something like, let's say, 13 plus 14 teeth, or perhaps 12 plus 15 teeth. But you notice now that in this case I already have significant undercutting on both of the gears, and if I go to a slightly higher reduction, closer to the reduction that I have here, then I get into even more undercutting. So a module 4 is basically out of the question simply because there cannot be enough teeth in that case. And so what we see here is that a module of 3 is the largest module I can get away with without running into the undercutting problem. And why do I want the largest module I can get away with? Well, that has to do with the fact that I have the most amount of leeway in the accuracy of the mounting of these gears, and at the same time I also have the highest amount of strength. So in this case, also because I don't care about backlash in this application, I don't care about what might happen if I reverse this screw pump, I simply don't care about this. I simply go for the highest module that is available to me. I did choose a pressure angle of 20 degrees for these gears, but looking back I could have probably selected 25 for the same result. One thing I haven't discussed yet is the outer diameter of these gears, which is something you'll need to know if you're going to fit them in a tight housing. So the outer diameter of a gear is simply the module times the number of teeth plus 2. And if you're in the inch standard system, you'll simply have the number of teeth plus 2 divided by the diametral pitch. Now, there is a nice way to rewrite this, which is simply by removing the parentheses. So you get the module times the number of teeth plus 2 times the module. And the nice thing about this is that this thing over here is simply the pitch diameter. And so if you look at a gear, what you essentially have is a pitch circle with a diameter of the pitch diameter, which is the module times the number of teeth. And then the outer diameter lies around that, and that is simply 1 time the module on this end and 1 time the module on this end. And so you also see that if the module is larger, there is a larger difference between the pitch diameter and the outer diameter. I hope you found that interesting and informative. If you have any questions or suggestions, please leave them down below. In the next video we'll take a look at helical and herringbone gears. Until then, thank you very much for watching and have a great night.